Today, we are going to talk about the growing memristor industry. First, I'm going to explain what is a memristor, its main applications, and the market size. Second, I'm going to describe how to make a meaningful investigation in the field of memristors in a university. And finally, I will present the conclusions. Memristors are two-terminal electronic devices with a metal insulator metal structure that can alter their electrical resistance between two or more stable states depending on the history of electrical impulses that are applied between the electrodes. The switching mechanism is normally governed by different physical phenomena, including phase change, or ion migration, or spin change, or ferroelectric dipole. Although this phenomenon has also been observed in many other materials, such as two-dimensional materials and perovskites, for example. Memristors are normally used as non-volatile electronic memory because they can emulate very well the ones and zeros of the binary code. However, it has also been proposed that they can be used for in-memory computing, for radiofrequency telecommunication, especially in the 5G and the 6G bands, and also for advanced data encryption. These are the main figures of merit of memristors. What most research articles normally report is sequences of ramp voltage stresses with different polarities. In this way, the authors can observe what is the resistance of the device in the high resistive state and also in the low resistive state, as well as which are the set voltage and the reset voltage. We always recommend to show the data in this way, overlapping many cycles, because then we can understand what is the variability of these parameters from one cycle to another and from one device to another. However, real applications of memristors don't work under ramp voltage stresses. They work under sequences of pulse voltage stresses. Because we need to evaluate what is the voltage required by the memristor to alter its resistance in a specific given time. And to do this, normally what is done is to apply sequences of pulses, such as read, write, read, erase, read, and then measure the current simultaneously. This also allows us to calculate what is the switching energy of the device, which is a very important parameter. There are another two very important figures of merit for memristors. The first one is called endurance, and it's defined as the number of times that a memristor can switch between two or more electrical states before one of them becomes permanent. And the other one is retention, which is defined as the time that one memristor stays in one state if only read pulses are applied. For multi-level memristors, typically used for in-memory computing, another important figure of merit has been defined, which is called potentiation and depression. This basically tells us how linear the transition of the memristor between different states it is from the least to the most conductive and vice versa. Here you can see the structure of the flagship electronic memories that are being now commercialized. This is the structure of the non-volatile flash memory, and this is the one from the volatile dynamic random access memory and volatile static random access memory. All of them are built upon transistors, meaning that this has to be fabricated in the foundry because these front-end of line processes are very complicated and expensive. On the contrary, memristors can be integrated at the back end of line of the silicon microchips. And this is very interesting because this can be easily fabricated in a university. And moreover, here we can use many more kinds of materials. Let's say the restrictions in terms of contamination are much lower. In this pyramid, you can see the different types of memories that are being commercialized depending on their capacity and their access time. And here in this radar plot, you can observe the properties of three different families of memristors, those that are based on phase change phenomenon, ion migration, which are normally referred as resistive random access memory, and those that work under spin change, which are normally called magnetic random access memory. And you can see that based on this performance, they can fill different gaps of this memory hierarchy. Here on the top, you can see the name of the different companies that have been investing over the past few years in the field of memristors for each type of material. But I like better to classify electronic memories with this other plot, which give us information about the cost of the memory per gigabit. And this is very important because cost is one of the main parameters determining the chances of one electronic device to arrive to the market. If we are going to talk about commercialization of memristors, we need to take into account two different sectors. The first one is the one of standalone memories. In this sector, memristors normally compete with other non-volatile memory, and the flagship memory is the NAND flash. And as we can see in this table, the cost of memristors per gigabyte is much higher. This can sound a little bit counterintuitive because we have explained already that memristors are very easy to fabricate and they can be integrated in almost every microchip. Well, the main reason is related to the integration density. The NAND flash has already achieved over 200 layers, and also the memristors have the problem of a series transistor that needs to act as a selector and also to mitigate, to be used also as current limitation. Moreover, memristive circuits still require some peripheral circuitry, and also I have to say that memristors still have not been integrated in the most advanced technology nodes. They are normally combined with transistor circuitry in the 180 or 130 nanometer node. And some studies have integrated memristors with FinFETs, and there is one recent article in the last IDM conference from TSMC that integrated memristors with in the 7 nanometer node. However, many more studies in this direction are necessary. And the second one is that when fabricating memristors, we need to alter the whole semiconductor industry in terms of materials, suppliers, third-party services, and some available infrastructure, because sometimes you need specific equipment to do that specific process. And therefore, this requires an initial investment that some companies are not willing or able to do. And the second sector is the one of embedded memories. And here the panorama is a little bit different. The only contender for the non-volatile embedded memory market is embedded flash. However, embedded flash show inconveniences in terms of high operation voltages and high energy consumption. Moreover, the price of memristors is already quite competitive, even lower than the one of embedded flash. And therefore, here we start to see some chances of success. Competition with SRAM is a little bit more difficult, but also because this is a volatile memory that is employed in different applications. Some memristors may reach the point in which they could replace SRAM in different applications, but this is a longer term war, at least from the point of view of cost. Here you can see some images of memristive products, and in this graph you can observe what is the tendency in the market for three different types of memristors, those based on phase change, ion migration, and spin change. It is interesting to see that the standalone market has declined significantly around 2022. The main reason is that Intel announced that it was going to wind down their manufacturing plant in Utah for phase change memristors. However, this tendency is starting to increase again. But the most spectacular and the biggest chances for memristors are in the field of embedded memory. And here, a massive growth is expected in the next few years, which is going to happen mainly in the field of microcontrollers for smartphones, laptops, cars, and all kind of home electronic products. But the history that memristors are coming, you may have heard it already a few years ago. And why should we trust that this is going to happen now? Well, in the past few years, memristors have been investigated by research groups and by some companies. But in fact, the factories were concentrated on scaling down the transistor. However, it is now and not earlier that they are facing massive difficulties. The first one is that there is no way to keep scaling down the embedded flash memory because it starts to require a very high number of additional lithography steps. There are also some rapid thermal oxidation and nitridation steps that require high temperatures, and this can affect the thermal budget of the whole process. And also, they require additional circuitry, especially charge pumping circuits that adequate the application of the voltage to the memory. On the other hand, in the field of SRAM, we have observed an stagnation of the minimum size that has been achieved at around 0.02 micrometers square. And this is also one possibility for memristors to penetrate in this market. Furthermore, there are new applications that are being proposed for memristors, not only memory, especially in the field of in-memory computing and neuromorphic computing. Here you can see a roadmap about the geometry of these transistors, how it is expected to evolve with the years, and you can see that they are becoming much more difficult to fabricate. And in fact, there are every time less and less factories that are able to fabricate this kind of devices. Therefore, this is also an opportunity for memristors because they can fabricate very easily in any laboratory. So as we mentioned, there are new applications. One of them is artificial intelligence, which is already arriving to our lives, making us more productive and also improving our quality of life. In artificial intelligence, the information is divided in different units, and this information is processed doing massive amounts of mathematical operations. One of the main building blocks is the perceptron, which has several inputs. The value of each input is multiplied by one specific number, which is normally called weight, and all these weights are then summed. This is something very similar to a vector matrix multiplication. After that, there is a comparison with a threshold value, and if the value of the sum is higher, then one output is activated, normally using a sigmoid function or another mathematical operation. Well, the problem is that doing so many mathematical operations with standard traditional transistor-based circuits is very time-consuming and very energy-hungry because you need to transfer the data from the memory to the central processing unit for every mathematical operation. And this has resulted in massive amounts of energy consumption and cost when you try to train large language models, such as, for example, the ChatGPT. However, it has been proposed that the vector matrix multiplication can be done with an array of memristors if they are able to show different stable states with a quite linear transition between all these states. These multiplications are done simply by Ohm law, and the sums are done by Kirchhoff law. And the activation function can also be done with memristors because if we change the materials that form the memristor, the transition can follow a very non-linear shape. And also, this low resistive state can relax, leading to a very well-defined hysteresis, which is something that it is necessary for these activation functions. In this article, there is one very nice example of one circuit that consists of 8 perceptrons in parallel. Each perceptron is a column. You can see the 8 inputs, and here in each node, there is one transistor with one memristor in series. This memristor needs to show multi-level resistive switching with linear transitions. So the authors employed tantalum, hafnium oxide, and palladium materials. And for this other memristor, which needs to serve as a neuron and shows very good nonlinearity, the authors employed silver electrodes and silicon dioxide as dielectric. Already some small prototypes have been fabricated, and it has been demonstrated that they can achieve an energy efficiency in terms of number of operations per watt that is 2 to 3 orders of magnitude higher than that demonstrated by NVIDIA graphic processing units. However, this has been done in small systems, and now we need to work to try to scale this up and make larger computations. Another interesting application of memristors is the use as radio frequency switch. And it has been demonstrated that if the memristor has a resistance in the low resistive state that is below 50 ohms, then one microwave can be transmitted. And in the high resistive state, the microwave can be blocked. And this is very interesting because state-of-the-art radio frequency switches are normally very big, and the memristor here has a very important opportunity to replace them. The main challenge in this field is endurance, because switching with very low resistance is something a little bit complicated and dangerous, and the structure of the insulator can be damaged. But important progress has been done in the past few years. And another application is in the field of encryption. Ideally, all the memristors in one microchip should switch at a similar voltage, the similar time, and they should show stable currents without fluctuations in each resistive state. However, as you can see in this plot, this normally does not happen. There is a variability of these parameters. So it has been proposed that if we compare the value of one cycle with the mean value or expected for the device, one can have randomly values that are above or below. And with this, you can generate true random number generators like those that we use when we make online purchases. So this is something quite attractive that requires many more research, because even if the memristors are already in the market as non-volatile electronic memory, increasing the performance and reliability will increase this market segment. And also for the other three applications that I mentioned, in-memory computing, radio frequency switches, and encryption, these products still need to be improved. And therefore, investigation at the materials level is necessary. The way in which research of memristors is being done has three main players. The first one are the foundries, which have access to the most competitive front-end of line fabrication. Second one is research centers, which they possess know-how, testing vehicle, and specific facilities to facilitate the integration. And the third one are startups and universities that can do more innovative experiment, try new materials that will be restricted in the other two players. In this table, you can observe one summary of most of the startups working in the field of memristors and the budget that have been raised by each of them. So this is really a growing industry that is giving jobs to many people. Before moving forward, let me describe the type of memristors in which I am working. I work mainly with memristors based on ion migration, and the main reason is that they are the easiest to fabricate compared to those memristors based on phase change and on spin chains. So in this domain, we have made a literature review to understand what are the materials that have been employed for this type of memristors. And most of them are insulating materials with band gaps normally higher than 4 electron volts. But in fact, not many materials have been tried. If we check, normally the industry has tried a few metal oxides. This table here only shows works that report integration of the memristor on the chip. And normally on the chip, studies only reported the performance of tantalum oxide, hafnium dioxide, and a few materials more, like silicon dioxide, aluminum oxide, and titanium oxide. But many other materials that have exhibited good performance in research articles, such as, for example, amorphous carbon, have still not been tried on chip, and therefore many more studies are necessary. And here, for this type of devices, we can recognize mainly two challenges. The first one is the variability from one cycle to another. So for these devices, the switching mechanism is based on the application of an electrical field between the electrodes. And when this happens, a conductive filament based on ions, normally from the electrode, is formed. When the polarity of the electrical field is reversed, this filament can be partially broken, and this leads to the high resistive state. Well, the problem is that when we do these many cycles, we see that there are important variations in the resistance that can be reached in each transition, because controlling the shape of the filament with these pulses is not easy. Moreover, after a few thousands of cycles, we can observe that the devices tend to die in the low resistive state. And the reason is that this conductive filament can propagate laterally, and it can arrive to a point in which it cannot be partially disrupted anymore. And this makes it impossible to reach the high resistive state. So we have to do experiments to try to tackle these issues. And here I would like to give two good practice recommendations, which are very important. The first one is use devices that are small as possible, and if possible, integrate them on the chip. And the reason is the following. When you have a specific material, like a metal of size, like those that I have described, these materials have a given density of defects. If you fabricate devices with a big top electrode, the density of defects will be higher than in small devices, just by probability and statistics. So if the device has more defects, normally the voltage that you need to apply to trigger the dielectric breakdown is lower. In the smaller devices, is larger. This happens for all the materials. It's a universal behavior. And if the voltage that you need to apply in the higher devices is lower, it will lead to conductive nanofilaments that have a different shape. And it is very common to see studies that are able to report good resistive switching in large devices, but not in small devices. And this is something very, very important. The second good practice is to employ correct measuring protocols. Most electronic, and this is particularly important when characterizing the endurance and the retention time. For in the specific case of endurance, this is the typical figure of merit that is presented in most articles in the field of memristors. They report one data point for the resistance in each cycle for a few given cycles within a large population of cycles up to millions. So you end up with a plot that first applies to only one device, and second contains very few data points. And this cannot be done, as I will explain in the next slide. But what is the correct mechanism to characterize the endurance of devices? Of course, when we try to do this at an industrial level, we need to measure the resistance in all the cycles for thousands of devices and make statistics. This is more necessary when you try to fulfill qualification processes. However, it will not be reasonable and possible to do this by an academic group in a university. You need probably specific tools, and it is a test that will take a very long time. So I recommend not to use one extreme, not to use the other. Something that is acceptable is to characterize the resistance in every single cycle for a few devices. This will be already enough and reliable enough, let's say. But why using this kind of figure of merit is not possible? Well, when we apply pulses, it could happen that if the pulse is too large, it can damage the device. And if it is too short, the device does not switch. And this can happen in one cycle and not in the following one. So you have seen a lot of studies that report some instabilities. They stop to switch for some cycles, then start to switch again, suddenly without any previous symptom of failure. And for this reason, We cannot do like this. We have to do like this. But what is the correct protocol to do like this? First, apply sequences of read, write, read, erase, read pulses and measure the current with a very high temporal resolution to understand how the current shape looks like during the read pulses. Then you can skip many points and read only one time during the read pulses. And this allows you to collect data for many more cycles because in the first test, you fill the buffer of your measuring equipment very fast. But here you can measure thousands of cycles and you can construct this endurance plot with the data of every cycle for one device. After you have this plot, you just need to repeat it for several devices. And many authors complain that they cannot do this because it will take very long time. In fact, if you apply pulses with a duration of 1 microsecond and with an interval of 1 microsecond, measuring 10 million cycles takes only 1 hour. So for us, this is not an excuse. Of course, if you want to measure much higher endurance, like 10 to the 9 or 10 to the 12, here it is necessary to skip some points, otherwise it will take a very long time. So here we have made a literature analysis of what is the endurance reported in different publications. And we compare the values of endurance given with the device size employed in that study. We use circles of squares depending on if the study has implemented the memristor on the chip or just fabricated it on a dummy silicon dioxide substrate. And we use field symbols if they stress and read in every cycle, and empty symbols if they only use a few data points. And also we use different colors depending on the number of devices that have been tested. And under this criteria, the ideal situation will be to have a red field circle in the top left corner. However, as you can see in this graph, very few studies have managed to do this. And if you want to see the whole table with the studies that we have analyzed, you can find it in the supplementary information of our recent comment paper in Nature Reviews Electrical Engineering. There is another interesting study that has compared what is the endurance claim for those works that analyze just one single big device and for those studies that make an array with small devices. And you can see that the differences in endurance are huge. So we always recommend to study devices that are as small as possible and integrated in the microchip. For the retention, this is also a big problem, the measuring protocol. Many studies measure few thousands of cycles and they extrapolate that this tendency will be maintained for 10 years. This is not the right way to do such a reliability prediction. These kind of predictions are normally made using the Arrhenius plot, which consists on measuring the endurance at many different high temperatures, and then this 10 can be extrapolated. So here we have made a similar analysis and we observe that very few studies have used the right measuring protocol with devices integrated on chip, and still the endurances achieved, the retentions achieved are not ideal. So more investigations in this direction are necessary. In this slide, I am summarizing the most important research directions in the field of memristors. The first one is to try to improve the endurance and the retention time. Second one is to try to reduce the switching voltages and the state currents. This will facilitate the integration in the chip and also will reduce the energy consumption. The third one is to try to reach reliable multi-level memristors for in-memory computing. So this implies reducing the noise and the drift of the current and test many more devices. Develop simulation tools that are more realistic, that they can consider line resistance, voltage drop, and also that combine the memristor with some peripheral circuitry. Realize full hardware implementation, combining the memristors with some transistor-based circuits, increase the integration density, doing more layers, avoiding the use of the serial transistors, and integrating the memristor in smaller technology nodes. And finally, reduce the insertion point of the memristor in the back end of line of the microchip. In one of the examples that I showed you, they integrated the memristor in the fourth metallization layer, but it will be ideal that it is closer to the transistor. In general, it is very important to report data for many more devices, indicating how many of them work, how many of them fail. And when they fail, it is important to report if they fail in open circuit, or if they are simply shorted, or if they show another characteristic that deviates very much from what is expected. You can see one very good example of this kind of variability and yield report in the supplementary note number 4 of this paper from the group of Professor Andras Kiss. And if you want more information about how are the qualification processes for memristors to reach different commercial applications, you can also check these other two references. I also would like to announce that our group is making several tape outs to fabricate testing vehicles for memristors. Here you can see an example of the layout of the microchip that we are fabricating. I have to say that the fabrication of this type of testing vehicles is a little bit particular. It is not possible to do this through a multi-project wafer tape out because these microchips come with a passivation layer, and this has to be removed in order to integrate the memristive material in the microchip. And this is something very problematic because these chips normally don't come planarized. So basically, what we recommend and what we have done is to fabricate a set of wafers and tell the foundry to stop them in one specific step of the fabrication. In our case, it's in the fourth metallization layer, and then send us the sample without passivation. In this way, when we receive the sample, it will be a little bit oxidized and contain some contaminants, but we have already demonstrated in a previous article published in Nature in 2023 that this can be overcome, this oxide can be etched, the samples can be cleaned to expose the vias, and then here one can integrate bottom electrodes, resistor switching medium, etc. In fact, I will explain this in my next video. So if you are interested in collaborating with us in this direction, you can send us an email and we will send you some testing vehicles to you for free so you can integrate your membristic material. So as a conclusion, I would like to say that memristors industry is consolidating due to the growing need for embedded non-volatile memory, and that in this sector, the price of memristors are becoming quite competitive. The second one is that if you are going to do research in your group, in your university, do what you want, but do it on the chip. It is much better. The technology readiness level increases a lot. And if you find something positive, some good performance, it will take you less efforts to try to bring it into the market. And finally, we are distributing microchips for memristor testing to the community. So if you are interested, please send us an email. Here I leave you some articles in case you want more information. This is a very nice review article commenting about some of the topics that we have described in this video. Finally, I would like to thank to all my team members for their hard dedication in every day in our laboratories. And just to communicate that if you are interested in joining my group at the National University of Singapore, you can apply to one of the job offers that we have published. We normally use the platform Web of Talents because this includes video webinars of the candidates, and it allows us to rank and filter the candidates according to relevant key performance indicators. And if you are a candidate, and you are not selected by our group, you have to know that if you register in this platform, your profile will be visible for other professors and recruiters. Therefore, you are maximizing your chances of getting a position. That's everything I wanted to share with you today. Thank you very much for your attention.